This lecture is about normalization and long normal form or global completeness. So first let's talk about normalization. So previously we introduced two new judgments, a up arrow for normal judgment and a down arrow for neutral judgment. So this neutral judgment was an auxiliary judgment that was introduced to define this notion of normal judgment. And if you have a proof of this normal judgment, we say that there is a normal proof of this judgment. And we'd like to formalize this idea. So there are two properties of this normal judgment. The first is the soundness, which says if there is a proof of a up arrow, then we can find a proof of a true. And the completeness says the converse. If a true is provable, then you can find a normal proof of it. So this soundness is actually easy to show because whenever you have a proof of this a up arrow, so you have a up arrow, a proof of this a up arrow, then you can just visit every part of this derivation tree and convert a down arrow into a true and a up arrow, let's say this is the C true. You can replace a up arrow with a true, and eventually you can convert the whole derivation tree into a proof of C true where no detour is found. So this soundness property says if there is a proof of this normal judgment, then you can convert this normal judgment proof into a proof of this truth judgment with no detour. So the proof is straightforward. And what about the completeness? Completeness says whenever there is a proof of this truth judgment, then you can find a corresponding normal proof. And this can be shown with, this completeness can be shown with this normalization theorem. So this normalization theorem says for every proof of a truth judgment, a true. So we have this a proof of this truth judgment. There exists a sequence of local reductions. So there exists some sort of local reduction, a sequence of local reduction. You apply local reduction. So you keep applying this sequence of local reductions. And this local reduction lead to eventually this sequence of local reductions lead to a normal proof of the same judgment. So after we apply this sequence of local reductions, we have proof of the same judgment, but here there is no detour. And if there is no detour in this derivation tree, we can easily convert this one into a proof of a up arrow. So this normalization theorem says for every proof of a true, so we have this derivation tree, we can find a certain sequence of local reductions, okay, that produce a proof of this normal judgment or a normal proof where no detours are found. So this is the normalization theorem, which effectively proves this completeness property because once you obtain this normal proof with no detour, you can easily uh, construct a proof of this normal judgment. Just visit every part of this derivation tree and annotate it with either a up arrow or a down arrow. Then you can construct a proof of this normal judgment without any clash. But the assumption here is for now, we make this assumption that we don't consider this disjunction and bottom. So we will come back to this issue later, but for now, let's assume that there's no disjunction and there's no bottom. And remember that this bottom is just a special case of generalized disjunction. It's a nullary. This bottom is actually nullary case of disjunction, right? So this normalization theorem in its current form is valid only without this disjunction and this bottom. Basically, it says that for every proof of a true, you can convert it after applying a certain sequence of local reductions. You can convert it into a normal proof. That's a normalization theorem, which essentially proves its completeness property. And there's another theorem which is called strong normalization. This strong normalization theorem says that you start with a proof of this truth judgment and you apply any sequence of local reduction. So this is local reduction. But the difference from this normalization theorem is, in the case of normalization theorem, we claim that there exists a certain sequence of local reductions. But in the strong normalization theorem, you can apply any sequence of local reductions however you want, but this strong normalization theorem guarantees that eventually this application of local reductions terminates with an equivalent proof with no detour. So this strong normalization theorem provides us with a simple strategy of converting this derivation tree into a normal proof. Just to keep applying local reductions in whatever order you want. And eventually, you will end up with a normal proof because this strong normalization theorem guarantees that this sequence of local reductions cannot proceed indefinitely. It should terminate eventually. So, and when it terminates, the resultant proof contains no detour. That is, we have found a normal proof. This is a normal proof. So that's a strong normalization theorem. The proof of this normalization property is left as an exercise in your upcoming written assignment. And in the video lecture, I'm going to give the key idea behind the proof of this normalization theorem. Now, let's get rid of this assumption of no disjunction and no bottom. So in other words, let's consider the full proportional logic with all the logical connectives. And it turned out that this normalization theorem and this strong normalization theorem in their current form, these two theorems are invalid in the presence of this disjunction and bottom. So we needed to fix the proof somehow. So first, let me show an example. Let me show an, Let me show an example that illustrates why this normalization theorem fails in the presence of disjunction and bottom. So what that means is that in the presence of disjunction and bottom, you have a proof of C true, and you keep applying a sequence of local reductions, but you will not be able to, it may be that you can never find a normal proof of this judgment just by this sequence of local reductions alone. You have to throw in something new. Without this something new, you may not be able to convert this ordinary proof into this normal proof with no detour. So let's figure out what what kind of conversion we should throw in, we should add to this sequence of local reductions. So here's a contrived example. So I want to show the A disjunction A implies A true. Of course, this is provable, but let me intentionally present a complicated proof with something unnecessary in it. So in order to prove this, we apply implication introduction rule. And now the goal is the proof of this A true. And now we have A disjunction, we have this assumption, 많이 갔나? We have this assumption A disjunction, A true. Let's call it hypothesis X. Now, we'd like to apply the elimination rule, disjunction elimination rule here. And we have two branches, A true, the first A true, and the second A true here. A true. Let's call it Y, W, Y, W. And normally, we would directly prove A true from this hypothesis. And similarly, we would prove A true, directly prove this second hypothesis. And then the conclusion would be A true, which immediately completes the proof. But let me add something unnecessary here, which is, for some reason, for some reason, I'd like to use this hypothesis twice. Okay, I use this hypothesis twice and prove a conjunction A true. So instead of A true, now we have a conjunction A true. This is the conjunction introduction rule. And similarly, for the second hypothesis, we use it twice and apply conjunction introduction rule. Now we have a conjunction A true. Then the conclusion of this disjunction elimination rule, YW, would be a conjunction A true. This is definitely unnecessary, but for the sake of argument, let's say this is the proof that we start with. But still, we can complete the proof because now it's just a matter of applying this conjunction elimination rule. Conjunction elimination rule, left. So this is, although this derivation tree is unnecessarily complicated, it's still valid proof. First, we can make two observations here. So observations. First, there's no detour there's no detour in this proof, where detour is defined as internal rule immediately followed by a corresponding elimination rule. So for example, conjunction introduction rule immediately followed by conjunction elimination rule. So we can see that there is no detour in this derivation tree. Well, we have this conjunction introduction rule, and we have a conjunction elimination rule here, and between these two inference rules, there lies this intervening disjunction elimination rule. So according to the definition of detour here, strictly speaking, this conjunction introduction rule is not immediately followed by this conjunction elimination rule because there is an intervening disjunction elimination rule here. So we cannot locate any detour, strictly speaking. So there is no detour in this proof. On the other hand, it's not a normal proof. If this if this is if there is no detour in this derivation tree, we would expect the proof to be normal, but it turns out that this is not normal proof either. It's not a normal proof. It's not a normal proof. And why is it that it's not normal proof? Let's try to annotate every part of this derivation tree either with the up arrow or down arrow. If we can, if we manage to replace this true judgment with a up arrow, then this would be normal proof. But we will see that our attempt eventually gets stuck. So this is an up arrow. Now this is a up arrow. Now this is a conjunction elimination rule. So therefore, from the viewpoint of this conjunction elimination rule, this one must be down arrow. So we would, for example, introduce a down arrow here and then apply this coercion rule. In this way, we keep annotating every part of all the parts of this derivation tree. So far, everything's fine. But what about this one? This was complicated, so let me erase this part. According to the disjunction elimination rule, this one must be up arrow. But that's fine because this is a hypothesis, so it's a down arrow. But we can convert it to up arrow with this coercion rule. But now, from the viewpoint of this disjunction elimination rule, this one should be up arrow. But from the viewpoint of this conjunction elimination rule, this must be down arrow. But there is no way to convert this up arrow into down arrow. This up arrow converts to down arrow. So this is not feasible because we don't have this rule. So if we attempt to annotate every part of this derivation tree with either up arrow or down arrow, we get stuck here. From the viewpoint of the disjunction elimination rule, this should be annotated with up arrow. But at the same time, from the viewpoint of this conjunction elimination rule, it should be annotated with a down arrow. And there's no way to convert this up arrow into down arrow, unlike this one. So the conclusion is we cannot annotate this judgment with up arrow, which means that this is not normal proof. So superficially, it seems like these two statements contradict each other. The first statement says there is no detour, so it must be normal proof. However, the second statement says it's not normal proof. But there's something wrong with this derivation tree. And, and why do we have this conflicting statement? And it's because of the role that this disjunction elimination rule plays. If we think about this disjunction elimination rule, let's say we have something like uh, disjunction elimination rule, A disjunction B true, so A true, C true, we have B true as hypothesis, and then we have a C true, and then we can conclude the C true. This is disjunction elimination rule XY. And if we think about this inference rule, the only role that's the only role that this disjunction elimination rule plays in this derivation tree is starting from this hypothesis and starting from this hypothesis, we always obtain the same conclusion. That's all. So for example, we could divide another inference rule, something like this. I'd like to eliminate A disjunction B here. So this is a new form of disjunction elimination rule. And we have two branches, this branch and this branch. And all and eventually we produce a C true, and eventually we produce a C true. In this case, we could combine these two into the same judgment C true. That's what this disjunction elimination rule essentially states. But unfortunately, we'd like to use this inference rule, but it's syntactically unacceptable. It's just a syntax problem. So this syntax is not accepted using our notation. So therefore, we choose this one. So as far as this judgment and this judgment are concerned, this horizontal bar plays no role at all. Or we could imagine that the horizontal bar is drawn only up to here, but not here. So let's go back to the this inference rule, this derivation tree. So even though there appears like this inference rule intervenes between this conjunction introduction rule and conjunction elimination rule, essentially it does not lie between these two. Syntactically, it appears like this inference rule, this disjunction elimination rule, lies between this conjunction introduction rule and conjunction elimination rule. But essentially, it doesn't. It only stays here. It only appears here. This is disjunction elimination rule. And that's the syntactic limitation of the notation that we borrow. The conclusion here is we needed to rewrite this derivation tree so that this disjunction elimination rule does not interfere with the interaction between this conjunction introduction rule and this conjunction elimination rule. In other words, we would like to interpret this instance as detour, introduction immediately followed by the corresponding elimination rule, even though syntactically there lies this intervening disjunction elimination rule. So syntactically this is not detour, but we'd like to be able to interpret this one as a detour, intro followed by elim. So we need some other conversion, some new conversion which allows us to bypass this disjunction elimination rule and combine this one and this one into detour. So this observation gives commuting conversion. What is called a commuting conversion? So the commuting conversion, so remember that this commuting conversion, whatever it is introduced to nullify the effect of disjunction elimination rule that lies between, for example, here conjunction introduction rule and here conjunction elimination rule. As a see through, see through. So syntactically, this is not detour because intro is not immediately followed by conjunction elimination rule. There's something else. But essentially, this is just as good as a valid detour. So we'd like to get rid of this one and combine these two. So that's what is provided by this commuting conversion. So the commuting conversion looks like, suppose that we have a disjunction B true, and we eliminate it, A true, is a 2, C true, and B true is 2, C true. And here we have another inference rule, C true, bottom C bar C prime true. So we have some rule R here. And we'd like to move this rule R upward, up here, above this horizontal bar. So we'd like to move this one over here so that we can combine these two inference rules as a detour. So the commuting conversion converts this one into, so basically we'd like to move this one, this inference rule up here. So after commuting conversion, we have A disjunction B true, and here we have A true, and we have C true. We can just make a copy of this partial derivation tree up here, and then apply the rule R, not here, but right away. This is the C bar true, and similarly, we can extend this derivation tree with an application of this rule R to produce C prime true. And now this is a valid application of disjunction elimination rule, and the conclusion is now C prime true. So the conclusion does not change. Here the conclusion is, the final conclusion is C prime true, and here the final conclusion is C prime true. So nothing changes except that now this inference rule directly binds to this judgment. So for example, if this was a conjunction introduction rule and this was a conjunction elimination rule, now we can apply local reduction to get rid of this detour. That's the basic idea. So this is the commuting conversion for disjunction, and there's also commuting conversion for bottom, which is left as an exercise. Now let's go back to this example. Now it's easy to see once we move this conjunction elimination rule up here, okay, then it would have just like a up arrow. Then we can get rid of this conjunction elimination rule. Now we can get rid of this part with local reduction. So we can now state the normalization theorem. Okay, so previously normalization theorem said for every proof of this truth judgment, for every proof of this judgment, there exists a sequence of local reductions that produce a normal proof of a true. So in other words, if we have a proof of a true, then there exists a certain sequence of local reductions that eventually produce another proof with no detour, or this normal proof. And this statement is valid only without this disjunction and bottom. But in the presence of this disjunction and bottom, we have to we might have to add some sort of uh, committing conversions. So now we have to say there exists a sequence of local reductions and commuting conversions. Committing conversions that lead to a normal proof of the same judgment. So that's the modified final version of the normalization theorem. And this committing conversion may appear to be complicated, but actually it's a pretty simple concept. So the best way to present the idea of a committing conversion is to show this reordering of left bindings. So for example, let's say we have this left binding in ML program. So left x equals left y equals E1 in E2. Uh-oh. E2 in E3. So it's pretty easy to interpret what this statement does. So you bind the result of E1 into variable y, and then you compute the expression E2. And then the result will be stored in variable x, and then you compute the expression E3. So it's very easy to see what this program does. And if we think about this, we can reorder these left bindings so that we have something simpler. So first compute y from expression E1, and then let's compute x from expression E2, and then finally compute the E3. So if we compare this program and this program, we can see that these two programs are essentially equivalent. And the idea is basically commuting conversion. So this is an analogy that we can draw in programming languages. So now let's move on to the second topic, long normal form. Long normal form or long normal proof. But so the whole motivation for studying normal proof is we'd like to find normal proof out of millions of different proofs for the same judgment. For the same judgment, the A true, we might have billions of different proofs because these proofs can include detours. But instead of um, these variations of essentially the same proof, we'd like to present some kind of a standard proof that is normal proof. Then one might expect that for every provable judgment like a true, there exists a unique normal proof. If that was the case, this notion of normal proof would serve its original purpose. Now, for if instead of these billions of different derivation trees, we can present a unique simplified, unique simple, normalized standard proof for the same judgment. Unfortunately, this is not the case. That is, for the same judgment A true, we might have two distinct normal proofs. So this one and this one is different, but this is a normal proof, and this one is also normal proof. Here's an example. The key here in the discussion of a long normal proof is this conversion rule. A down arrow is converted to A up arrow. This is conversion rule. And there's no other side condition. A can be any proposition, not just atomic proposition, but also it can be a composite proposition. So let me show an example. The example is simply A implies B implies A implies B up arrow. We can present two different proofs for this normal judgment. A implies B implies A implies B up arrow. And the first rule is the first derivation tree simply applies implication introduction rule, and A implies B down arrow hypothesis is directly converted to A implies B up arrow. That's all. So there's nothing wrong in this derivation tree. If we imagine the hourglass here, the middle of the hourglass is a kind of wide. It's not quite narrow because this A implies B, a composite proposition is converted. In the second derivation tree, we'd like to have some narrow middle. The middle should be narrower. And the idea is we do not convert this A implies B down arrow directly. We further decompose this thing into atomic propositions. So here's the derivation tree. A implies B up arrow, and we assume A implies B down arrow. And instead of converting this one into this one directly, this time we'd like to apply implication introduction one more time. So now we have A down arrow, and with the new goal is a B up arrow. And this one can be converted to A up arrow with this coercion rule. And now we apply implication elimination rule to deduce B down arrow, which is converted to B up arrow. So this is also valid normal proof for the same truth judgment. So this one and this one, they are both valid normal proofs. But our intuition says this is closer to the standard, the ideal normal proof. And if we imagine the hourglass, then the middle of this hourglass is much narrower than this one, because now we decompose this one further until we have only this atomic proposition. So this doesn't look like a standard, and our intuition says this looks like standard, or this looks closer to the standard proof that we'd like to have. So in order to enforce the conversion on atomic propositions only, rather than these composite propositions, we'd like to place a new restriction on this rule, which is in, instead of this one, okay, A down arrow is converted to A up arrow with a side condition, A must be atomic. So now we use this conversion rule instead of this one. With this rule, this one is no longer valid because here we attempted to convert this composite proposition. Here we convert this B down arrow and B is atomic. So this is now valid, okay, but this is no longer valid according to this coercion rule. And we say that and we say that a proof, a normal proof, say proof of C up arrow, where we use this new coercion rule with the new coercion rule, this coercion rule with this restriction that A must be atomic. We say that this proof is long normal proof. It's long. It's longer than this one. This is longer than this one. Intuitively, here we take a shortcut. We take a shortcut of converting A implies B down arrow directly to A implies B up arrow. But here we are taking longer path because we further decompose this one into B down arrow. So this is long normal proof, whereas this is not. So now we have learned the notion of long normal proof. And the question is, why do we bother with this notion of long normal proof? And the reason is, this notion of long normal proof directly addresses the issue of global completeness. Recall that this local completeness, so we learned this local completeness or eta expansion or uh, local expansion, all this stuff. This local completeness says that elimination rule for a particular logical connective, for example, elimination rule for conjunction, like conjunction elimination rule. This specific elimination rule is strong enough. This rule is strong enough so you can safely apply this elimination rule and you lose nothing. No matter how many times you apply this conjunction elimination rule, you don't lose nothing. You can recover everything that you had previously. But this one only discusses the property of a particular elimination rule. In contrast, this global completeness property says all the elimination rules collectively. So it turns out that with this rule is actually enough because we can show that the original coercion rule, this is the original coercion rule, and this is a modified, more restrictive coercion rule. And there's no difference because we can show that this inference rule is derivable from this one. So as far as the expressive power of the logic is concerned, this rule is actually unnecessary because we can simulate every part of this inference rule with this modified, more restrictive coercion rule. So the bottom line is this is all we need. We never need this one. This is all we need because this is derivable. So what this means is that now if there is normal proof of some judgment, so for example we have this hourglass shape of this normal judgment. So this is normal proof. And because now we require that the the proposition in the application of this coercion rule be atomic. So this must be atomic now. What that means is that we have a bunch of hypotheses here. Let's just say A1 down arrow, AN down arrow, and we keep applying elimination rule. And in order to convert this down arrow into up arrow, so in the middle we apply this coercion rule. But this one must be atomic now. So what that means is that in order to build a normal proof, now you have to keep applying elimination rules until no more elimination rules can be applied and only these atomic judgments remain. Sorry, only atomic propositions remain in this neutral judgment. So for example, if you have, say, A implies a B down arrow, you have to keep applying elimination rule. So now every normal proof looks like this, where in the middle we apply this coercion rule to atomic proposition. And what that means is that we can apply this elimination rule, any elimination rule, not just a single particular elimination rule. We can apply all elimination rules in any order until no more elimination rules can be applied. So basically, we keep applying all these elimination rules without having to worry about losing anything. We don't lose at all. We don't lose anything at all. So therefore, we can conclude that these elimination rules are strong enough. It's just a matter of keep applying these elimination rules. We don't lose anything. We can still recover anything that we start with. Let's say we start with this one and we recover essentially the same information. So in this regard, this this property, the property that this new coercion rule is okay, this new coercion rule is enough. Essentially, this property indicates that these elimination rules, not just the single elimination rule, but all these elimination rules are collectively strong enough. So that means it's global completeness. Now the remaining issue is global soundness. And we will tackle this problem in our discussion of sequence calculus.